The weight of the blankets against your legs, the gentle pressure of your body settling into the mattress, the slow rise and fall of your chest as you breathe. That feeling, that quiet holding, is the first thing we know about gravity. Long before we have words for it, long before anyone explains what it is, we feel it. A baby lying in a crib feels it. A cat curled at the foot of the bed feels it. It is the most familiar thing in the world, and yet, in some ways, it is also one of the most puzzling things physics has ever tried to understand. And that is what we are going to do together. Very slowly, over the next little while, we are going to untangle the confusing parts of gravity, one at a time, with no rush at all. There is nowhere to get to. There is nothing to solve tonight. We are simply going to sit with this force, this pull, this bending of the world, and let it become a little clearer, piece by piece, like watching a slow cloud drift apart in a dark sky. Right now, in this moment, gravity is doing something remarkable. It is holding you. Not just pinning you down against the bed, not just keeping the bed from floating up off the floor, but actually pulling on every single part of you, gently, steadily, in a way that has been going on since long before you were born and will continue long after. And what is strange, when you stop to think about it, is that this pull never turns off. It never takes a break. You do not have to do anything to earn it or maintain it. It simply is. The earth and your body are in a kind of quiet conversation, a mutual attraction that has been unfolding for your entire life, and you have been part of it without ever having to think about it. Tonight, we are just going to think about it a little. Not in a way that demands anything from you, not in a way that expects you to remember every detail, just in a way that lets the ideas drift through your mind, like leaves moving on the surface of a slow stream. Let us begin with the simplest thing, the thing you are feeling right now. Gravity is a force, and among the 4 fundamental forces that physicists know about, gravity is the one we notice most in our everyday lives. There are 4 of these forces in total, the basic ways that everything in the universe interacts with everything else. There is the strong nuclear force, which holds the centers of atoms together. There is the weak nuclear force, which plays a role in certain kinds of radioactive decay. There is electromagnetism, which is responsible for light, for electricity, for the reason your hand does not fall through a table. And then there is gravity. Of these 4, gravity is by far the weakest. Not just a little weaker, vastly, almost unimaginably weaker. A tiny refrigerator magnet can stick to a metal surface, and in doing so, it is overcoming the gravitational pull of the entire Earth. Think about that for a moment. A small magnet, something you can hold between 2 fingers, can lift a paperclip up off a table, and in that simple act, the electromagnetic force in that little magnet is winning a tug-of-war against the gravitational pull of a planet that weighs 6 sextillion metric tons. That is how much weaker gravity is. And yet, even though it is so much weaker than the other forces, gravity is the one that shapes the large-scale universe. It is the one that holds the moon in its path around the Earth. It is the one that keeps the Earth moving around the sun. It is the one that gathers stars into galaxies and galaxies into clusters. It is the one that never cancels out, never gets shielded, never goes away. The other forces can balance each other out. Positive and negative electric charges can cancel. But gravity only ever adds up. It only ever pulls. And because it pulls on everything with mass, and because there is so much mass in the universe, gravity ends up being the architect of the cosmos. So here we have this strange pair of facts, sitting side by side. Gravity is the weakest of the 4 forces, so weak you overcome it every time you lift a spoon to your mouth. And gravity is the force that built the stars. Both of these things are true. Both of these things are true. And holding 2 seemingly opposite ideas like that, without needing to resolve them right away, is one of the quiet skills that science teaches us. There is another pair of ideas that sits together, and it is important to say it early, before we go any further. Gravity is something we understand very well, in the sense that we can describe what it does with extraordinary precision. We can predict the path of a spacecraft through the solar system so accurately that it can arrive at a tiny, distant world years after it left Earth, exactly on schedule, exactly on target. We can calculate the bending of starlight around the sun. We can account for the tiny differences in the ticking of clocks on satellites. In all these ways, the mathematics of gravity works beautifully. And at the same time, there are deep, fundamental things about gravity that nobody fully understands. Physicists do not know why it is so much weaker than the other forces. They do not know how it fits together with the physics of the very small, the quantum world. They do not know what happens at the very center of a black hole, where the description we have breaks down. These are not small gaps. They are large, open questions that have been sitting patiently at the edges of physics for a long time. And this not knowing is not a failure. It is not something that needs to be fixed right away. It is just a fact about where we are in the long, slow process of trying to understand the universe. The not knowing is allowed to feel restful rather than frustrating. It is like standing on the shore of a vast ocean at night. You cannot see the other side. You do not know everything that is out there, but you can feel the sand under your feet, and you can hear the slow rhythm of the waves, and that is enough. So tonight, as we move through these ideas, we are going to hold both the known and the unknown gently. We are not going to pretend that everything is solved. We are not going to rush past the gaps. We are going to let them be there, the way you let the dark spaces between stars be there when you look up at the night sky. The gaps are part of the picture. They are what make the picture honest. Let us settle into this a little more deeply. Take a slow breath, if you like. Feel the weight of your body against the bed. That weight is gravity speaking to you in the most direct way possible. It is the earth pulling on your mass, and your mass pulling back on the earth, and the bed pushing up against you in response. All of that is happening right now, silently, without any effort on your part. Your body is doing what bodies do in a gravitational field. It is being held, and your body knows this. Your muscles are not tense because they do not have to fight to keep you in place. Gravity is doing that work for you. Your bones, your skin, the fluid in your inner ear, all of it is oriented to this steady downward pull. When you lie still like this, you are aligned with one of the fundamental forces of the universe. There is something quietly profound about that, something that does not need to be made dramatic to be meaningful. It is simply true. You are part of the same system that keeps the moon in its orbit and the earth in its path around the sun. The same force, the same pull. Right here, right now, in the dark. As we go on, we will pick apart some of the confusing pieces. We will talk about what falling really means, and why we do not feel the earth spinning under us, even though it is moving at tremendous speed. We will talk about why astronauts float, not because there is no gravity where they are, but for a different, more interesting reason. We will talk about how gravity bends light and slows down time. We will talk about black holes, calmly, without any of the drama that usually surrounds them. We will talk about the parts of gravity that do not fit with the rest of physics, the open questions that remain, and we will do all of this very slowly, with plenty of time to let each idea settle. You do not need to hold on to anything. You do not need to memorize anything. This is not a lesson that will be tested later. This is just a quiet walk through a landscape of ideas, taken at whatever pace feels comfortable. For now, as we prepare to move into the next part, let your attention rest on the simple sensation of being held. The blankets have weight because the earth is pulling on them. The mattress has shape because gravity is compressing it under you. The air in the room stays around you, rather than drifting off into space, because gravity keeps it close. Even the warmth of your body, the heat that rises from your skin, is moving through air that is itself held by gravity. Everything in this room is part of this quiet, steady attraction, and you, lying here, are at the center of it. Not the center of the universe, but the center of your own experience of gravity, which is the only gravity any of us ever directly knows. That personal center is enough. It is all you need to begin. In a moment, we will take the first small step into understanding what this pull actually is, starting with a very old idea, one that goes back more than 300 years to a man named Isaac Newton. His insight was simple and powerful, and it changed the way we think about falling. But before we go there, just stay here a little longer, feel the pull, let it be exactly what it is, without needing to name it or explain it. The pull that holds you to the bed, the pull that keeps the moon from wandering away, the pull that gathers galaxies, the pull that, right now, is as close to you as your own heartbeat. That is gravity, and that is where we are going, together, slowly, through the dark. And so we begin to step forward, very gently, into the first real question: what does it actually mean to fall? What is happening when something drops? When an apple leaves a branch? When a spoon slips from a hand? When a leaf detaches from a tree and drifts down to the ground? The motion is so ordinary we rarely stop to examine it. But inside that simple falling is the key to understanding what gravity actually does between two objects, anywhere in the universe. For a very long time, people thought about falling in a way that feels natural. Things fall because the earth pulls them down. The ground is the destination. The pull goes one way, and from the point of view of someone standing on the ground, that seems right. A stone dropped from your hand goes down. It does not go sideways, it does not go up. The earth calls it, and it answers, and that is the end of the story. This picture works well enough for everyday life. It is what your body expects. It is what your muscles and bones have learned since you were a child learning to walk. Down is down. The earth is the source of the pull. Everything else is just along for the ride. But this picture, simple as it is, misses something important. And the person who first saw the missing piece clearly was Isaac Newton, working in England in the 1600s. Newton's insight was quiet and deep. He realized that the pull does not go only one way. It is not just the earth pulling on the apple is also pulling on the earth. Every single thing that has what we call mass, every object that contains matter, pulls on every other thing. The pull is mutual. It goes both ways. The earth pulls on you, and you pull on the earth, at the very same time, with the very same strength. That is the core of Newton's idea. Gravity is not a one-way street. It is a conversation between two things. A quiet, equal conversation that happens between every pair of objects in the universe. Let us pause on that word, mass, because it is going to come up again and again. Mass is just a way of saying how much stuff, how much matter, is packed into something. A rock has more mass than a pebble. A planet has more mass than a rock. A star has more mass than a planet. Mass is not the same thing as weight, though the two words get mixed up in everyday talk. Weight is what you get when gravity pulls on mass. Your mass is the same on the earth and on the moon. The amount of matter in your body does not change, but your weight would be different in those two places, because the moon pulls on your mass less strongly than the earth does. So mass is the deeper thing, the more fundamental thing. It is the measure of how much you are made of. And it is mass that does the pulling in gravity. Everything with mass pulls on everything else with mass, no exceptions. So when you drop a small stone, the stone does fall toward the earth. That part is obvious. But the earth also falls, very, very slightly, toward the stone. They move toward each other. The reason you do not see the earth move is that the earth has enormously more mass than the stone. Enormously more. The pull on both is equal, but the effect is not. A small mass is easy to move. A huge mass is hard to move. So the stone does most of the visible traveling. It accelerates quickly toward the ground. The earth accelerates toward the stone too, but by such a tiny amount that no instrument in Newton's time could have measured it, and even today it would be too small to notice in any ordinary way. But the equality is there, in the mathematics. The pull is symmetrical. The stone and the planet are partners in the same dance, even if one partner is so much larger that it appears to stand still. This is a gentle thing to sit with for a moment. The idea that you are not simply stuck to the earth like a magnet to a refrigerator. You are pulling on the earth just as genuinely as the earth is pulling on you. When you stand up from a chair, your body pushes down against the floor, and the floor pushes back, yes, but in the gravitational sense, your mass is tugging on the whole planet, not in a way that would ever be felt, not in a way that shifts the orbit of the moon, but in a way that is real. The physics does not care how small you are. The equation works the same for a grain of sand and for a mountain. The force between you and the earth is the same size from both sides. It is a mutual attraction, a shared pull, a two-way bond that has been there since the moment you were born and will be there after you are gone, because your mass, the matter that makes you up, will still exist in some form, and it will still pull and be pulled. Now let us take another step into this idea of falling, because Newton saw something else that was just as important. He realized that if you could remove the air, if you could drop things in a perfect emptiness, a vacuum, something surprising happens. All objects fall at exactly the same rate. A heavy cannonball and a light feather, dropped from the same height in a place with no air to slow them down, would hit the ground at the same moment. This is not just a thought experiment. It was actually demonstrated, beautifully and simply, on the moon. During the Apollo 15 mission in 1971, an astronaut named David Scott stood on the lunar surface, which has no air, and dropped a feather and a hammer at the same time, and they fell together. Side by side, they hit the dust at the same instant. The hammer was much heavier, much more massive, but it did not fall faster. The feather, light as it was, kept right up with it. They fell as equals. This is one of those facts about gravity that can feel wrong in the body, because on Earth, in the air, a feather does not fall like a hammer. The feather drifts, catches the wind, floats sideways, takes its time. But that is not because gravity treats the feather differently. It is because the air pushes back on the feather more than it pushes back on the hammer. The feather has a large surface for its small mass, so the air resistance is strong. The hammer has a small surface for its large mass, so the air resistance is weak. In a vacuum, with no air at all, there is no resistance, nothing to push back. And in that pure environment, gravity shows its simple, elegant rule. Everything falls at the same rate. Every object, regardless of its weight, regardless of its mass, accelerates toward the ground at the same pace. Why is this? Why does a heavier object not fall faster? It would seem to make sense that if gravity pulls harder on a heavier thing, the heavier thing should speed up more. But there is a hidden piece here, and it goes back to mass. Mass does two things in physics. It is the source of the gravitational pull. More mass means a stronger gravitational pull. But mass is also a measure of something else. It is a measure of how much an object resists being moved. This is called inertia. The more mass something has, the harder it is to get it moving from a standstill, and the harder it is to stop it once it is moving. So a cannonball has more mass than a feather. That means gravity pulls on it more strongly. True, but it also means the cannonball resists being moved more strongly. The two effects cancel out exactly. The extra pull is perfectly balanced by the extra resistance. And so the cannonball and the feather end up accelerating at the same rate. They fall together. Not because gravity is treating them differently, but because the very thing that makes the pull stronger also makes the object harder to pull. The two effects are tied together in a way that Newton found deeply meaningful, and that later, much later, would lead Einstein to an even deeper understanding. Let that settle for a moment. Everything falls at the same rate in a vacuum: a grain of sand, a block of lead, a drop of water, a human body. If you could take a handful of different objects and release them in a chamber with no air, they would all fall side by side, as if they were a single thing. Gravity does not care what an object is made of. It does not care about its shape, its color, its temperature, its history. It only cares about mass. And it responds to mass in this perfectly balanced way, pulling harder on the heavy things, but also having a harder time getting them to move. The result is this quiet, universal falling, the same for everything, everywhere. On Earth, the rate of this falling acceleration has a number attached to it, but we are not going to dwell on the number itself. What matters is the idea. When you drop something near the surface of the Earth, and you ignore the air, the object speeds up as it falls. Every second, it gains the same amount of speed. It does not fall at a constant speed, it accelerates. This is why a fall from a greater height hits harder than a fall from a small height. The object has had more time to speed up, and this acceleration is the same for everything. The apple from the tree, the raindrop from a cloud, the leaf if the air were not there to slow it. All of them falling in the same rhythm, the same steady increase of speed, the same patient pull. This is the foundation that Newton gave us, a simple, powerful picture. Every object with mass pulls on every other object with mass. The pull is equal on both sides, and in the absence of air, all objects fall at the same rate regardless of their weight. These three ideas are like three quiet stones placed carefully in a stream. They are solid, they hold, and from them a great deal of understanding flows. With these ideas, Newton could explain the motion of the planets, he could explain the orbit of the moon, he could predict the paths of comets. His description of gravity worked so well that it stood unchallenged for more than 200 years. It is still used today for most everyday purposes, for engineering, for sending spacecraft to other worlds. It works. It is not the whole story, as we will see later, but it is the first and most essential part of the story. And there is something else worth noticing here, something that often gets overlooked in the rush to get to the more complicated parts. Newton's picture tells us that falling is not a special event. It is not something that happens only when an object loses its support. Falling is the natural state of things. When you hold a stone in your hand, you are interfering with its natural motion. You are preventing it from falling. The stone wants, if we can use that word loosely, to move toward the center of the earth. It is only your hand, pushing up against it, that stops it. When you let go, the stone is not starting something new. It is returning to what it would have been doing all along, if you had not been in the way. Falling is the default. Floating in space or resting on a surface is the interruption. This is a strange inversion of how we normally think about it. We think of falling as the unusual thing, the accident, the loss of control. But from the point of view of gravity, falling is the steady background state. It is what mass does. It pulls, and it is pulled. And if nothing blocks the path, the objects move toward each other. You can feel this in a small way when you lie very still. Your body is being pulled down into the mattress. The mattress is pushing back up. If the mattress were not there, you would fall. If the floor were not there, you would keep falling. If the ground were not there, you would fall toward the center of the earth. The falling is always present, always pulling, even when it is being blocked. It does not go away just because something is in the way. It just waits. And when you are lying still in the dark, you can sense that waiting. The potential for falling is always there, held back by the bed, held back by the floor, but never absent. It is as constant as your heartbeat, as steady as your breathing. So now we have a new way to think about what is happening in this quiet room. You are not just resting on a surface. You are in a mutual gravitational pull with the entire Earth. The Earth is pulling on you, and you are pulling back on the Earth with exactly the same strength. The bed is interrupting your fall. The floor is interrupting the bed's fall. The ground is interrupting the floor's fall. And all the way down, layer by layer, the fall is being passed along, held in check, waiting. And if you could remove all the air and drop a feather and a hammer, right here in this room, they would fall together, side by side, at the very same pace, and hit the floor at the very same moment. These are not complicated ideas. They are simple, almost childlike, but they are true, and they are the starting point from which everything else about gravity unfolds. As we move forward, we will leave this simple picture and gradually add to it, layer by layer. We will see how gravity works on larger scales, why we do not feel the Earth spinning, what weightlessness really means. But for now, let this first piece sit quietly. The mutual pull, the equal fall, the steady, patient presence of gravity, holding you here, being held by you in return, without effort, without noise, without end. That is what falling really means. And it is enough, for now, to simply know that, and to let the knowing drift softly into the background as you settle deeper into the dark. The steady, patient presence of gravity. That phrase lingers, and it leads us naturally to one of the most common puzzles people encounter when they first learn a few facts about the Earth. The Earth is spinning. It is also moving through space around the sun, and the numbers, when you hear them spoken aloud, sound enormous. At the equator, the surface of the Earth spins at roughly 1,000 miles per hour. That is faster than any car, faster than any train, faster than the speed of sound. And the whole planet, carrying us with it, is moving around the sun at about 67,000 miles per hour. 67,000 miles every single hour. These are not small speeds, and yet, as you lie here in the dark, you feel completely still. There is no sense of rushing, no wind from the spin, no lurch from the orbit. The room around you is silent and motionless. So how can both things be true at once? How can we be moving so fast and feel nothing at all? The answer sits in a very simple idea about how motion works, one that is easy to understand when you break it down slowly. Our bodies do not feel speed. Our bodies feel changes in speed. The word for a change in speed is acceleration. When your speed stays exactly the same, when you are moving at a constant pace in a constant direction, your body has no way to detect the motion from the inside. You need to look outside, at the world passing by, to know you are moving at all. This is something you have experienced many times without thinking about it. Imagine you are riding in a car on a long, straight, smooth highway. The car reaches a steady speed, maybe 60 miles per hour, and then just holds it. The engine hums quietly. The road stretches ahead, and inside the car, you feel almost nothing. You could close your eyes and, if the road were perfectly smooth and the speed perfectly constant, you would have no idea you were moving. You could be sitting in your living room. Your body does not feel 60 miles per hour. It does not feel the speed itself. What your body felt, earlier, was the moment the car sped up, when the driver pressed the gas pedal and you were pushed gently back into your seat. That was acceleration. That was a change in speed. And when the car slows down, when the brakes are pressed, you feel yourself lean forward slightly. That is also acceleration, a change in speed in the other direction. But the long, steady middle part, the constant speed, is silent to your body. It is a smooth, unbroken flow. No information reaches your inner ear. No signals go to your brain. Motion without change is invisible from the inside. This is exactly what is happening with the Earth. The Earth is spinning, yes, but it spins at a nearly constant speed. It does not suddenly speed up or slow down in a way we could feel. The spin is steady, unchanging, smooth beyond anything a car on a highway could manage. It has been spinning this way for billions of years, slowing down only very, very gradually, by tiny amounts over enormous stretches of time. The change is so slow that no human being could ever notice it in a lifetime. So the acceleration, the change in speed, is effectively zero as far as your body is concerned. The same is true for the Earth's orbit around the Sun. The orbit is an ellipse, a slightly stretched circle, and the speed does vary a little as the Earth moves along that path. But the variation is very small, spread out over a whole year. It is not a sudden jerk. It is not a lurch. It is a gradual, gentle shift that your body has no hope of detecting. So you feel still. You feel at rest. Even though you are spinning and orbiting at tremendous speeds, the motion is so smooth, so constant, that it disappears from your senses entirely. There is another piece to this puzzle, and it has to do with everything around you. When you ride in a car, you can tell you are moving, partly because you see the trees and the buildings sliding past the window. But when you are on the earth, everything is moving with you. The ground under the bed itself, the air in the room, the walls, the ceiling, the house, the trees outside, the atmosphere itself, all of it is spinning together. Nothing is left behind. Nothing is still while you move past it. The entire planet and its blanket of air are rotating as one. So there is no window to look out of, no visual cue that would give away the motion. Even if you stood outside and looked up at the stars, the motion is so smooth that you cannot feel it. The stars do appear to move across the sky over the course of a night, but that motion is too slow for your eyes to perceive in the moment. It is like watching the hour hand of a clock. You know it is moving, but you cannot see it move. The Earth's spin is the same kind of slow, steady turn when viewed from the surface. Too slow to see, too smooth to feel. And this is where gravity comes back into the story, because gravity is the reason everything moves together. Gravity is what holds the atmosphere against the planet, pulling the air along as the Earth turns. If gravity were to switch off, the air would simply drift away into space, and the ground would fly apart, and all of us would be thrown off into the void. But gravity does not switch off. It holds the air close. It holds the oceans close. It holds the soil and the rocks and the trees and the buildings and your body close. Everything is bound together by this mutual pull, and so everything rotates as a single unit. There is no wind from the spin because the air is spinning with the ground. There is no sense of being dragged because the ground, the air, and your body are all moving at the same speed, in the same direction, together. You are part of the system. You are not a passenger on a moving vehicle. You are a piece of the moving planet itself, held in place by the same force that keeps the planet whole. Let us sit with that image for a moment. Right now, as you lie still, you are spinning. The bed is spinning. The room is spinning. The whole block of the earth under you is spinning. And you are spinning with it, perfectly smoothly, perfectly quietly, without the slightest tremor or shake. The motion is so constant, so free of any change, that your body has no reason to register it. Your inner ear, the part of you that senses balance and movement, is designed to detect acceleration, not speed. It contains tiny structures, small tubes filled with fluid, and when your head accelerates, the fluid moves and triggers nerve signals. When you turn your head quickly, when you stand up too fast, when you ride in an elevator that starts or stops, the fluid moves and you feel it. But when the motion is perfectly steady, the fluid settles. It becomes still relative to the walls of the tubes, and when the fluid is still, your brain receives the message that you are not moving. That is what is happening right now. The fluid in your inner ear is still. It is spinning with you, at the same speed, so there is no relative motion, no signal, no sensation. Your brain, quite correctly given the information it has, concludes that you are at rest. And in a very real sense, you are. You are at rest relative to the room, relative to the bed, relative to the air. That is the only kind of rest that matters for your body. The larger cosmic motion is invisible to your senses, and so it does not disturb your peace. This same principle explains something else that can seem puzzling. The Earth is not only spinning, it is also orbiting the Sun at that enormous speed of 67,000 miles per hour. And the Sun itself is moving around the center of the Milky Way galaxy at a speed of about 500,000 miles per hour. And the galaxy is moving through space as well, drawn by the gravity of other galaxies and clusters. So you are not just spinning, you are not just orbiting. You are on a planet, orbiting a star, which orbits a galaxy, which moves through a cluster, which moves through the universe. The total speed, adding up all these layers of motion, is hard to even express. And yet, through all of it, the motion is smooth. There are no sudden turns, no jerks, no stops. The galaxy does not brake at traffic lights. The solar system does not swerve to avoid an obstacle. The movement is a long, slow, graceful arc through space, so steady that it might as well be stillness. The fluid in your inner ear knows nothing of it. Your skin knows nothing of it. Your bones know nothing of it. You are carried, silently, through the cosmos, with no more sensation of speed than a pebble resting at the bottom of a calm stream. There is one more subtlety here, a gentle one, worth touching on before we leave this idea. The Earth's spin does produce a very small effect that you might, in theory, be able to notice if you were paying extremely close attention. Because the Earth is rotating, the surface at the equator is moving faster than the surface near the poles. This creates a slight outward force, a centrifugal effect, that makes things at the equator weigh very slightly less than they would at the poles. A person who weighs 200 pounds at the North Pole would weigh about 199 pounds at the equator. The difference is tiny, less than 1%, and it is not something you would ever feel directly. It is just a gentle reminder that the spin is real, that it does have effects, even if those effects are far too small for your body to notice. The Earth is also not a perfect sphere. It bulges slightly at the equator because of this same spin, making it a little wider around the middle than it is from pole to pole. But again, these are facts that belong to measuring instruments, not to the quiet experience of lying in bed. For you, right now, the spin is invisible. The orbit is invisible. The galaxy's motion is invisible. All of it is smoothed over by the steady, patient hand of gravity and the nature of constant motion. So the puzzle resolves itself, and what felt like a contradiction becomes a quiet harmony. The Earth spins at 1,000 miles per hour. The Earth orbits at 67,000 miles per hour. The Sun moves at 500,000 miles per hour. The galaxy drifts through space at speeds beyond easy imagining. And you, lying here in the dark, feel absolutely nothing. Not because the numbers are wrong, but because speed is not a thing that can be felt. Only changes in speed can be felt, and the changes at these vast cosmic scales are so slow, so spread out over time, that they fall below the threshold of any living thing. You are moving faster than a bullet, faster than any human-made object has ever traveled, and yet you are perfectly still. Both things are true. The stillness is real, the motion is real. They sit side by side, without contradiction, held together by the simple physics of acceleration and the steady pull of gravity that keeps everything moving as one. And perhaps there is something restful in that. To know that the wild, rushing motion of the planet through space does not disturb your sleep. To know that gravity is not just holding you down, but also carrying you along, smoothly, silently, without the slightest bump or shake. The same force that gives weight to the blankets is the force that keeps the air from flying away, that keeps the oceans from drifting into space, that keeps the whole planet intact as it spins and orbits and travels through the galaxy. You are held, you are carried, and you feel none of it. The motion is there, immense and unceasing, but it passes through you like light through a window. Your body rests, your breathing slows, the Earth turns, and you turn with it, and in the quiet dark there is only the soft weight of the blankets, the gentle pressure of the mattress, the slow rhythm of your own breath. That is enough. That is everything. And as we drift forward, we will take this understanding of motion and stillness with us, because it will help us untangle the next piece of the puzzle, the strange truth about weightlessness, and what it really means to float. And so we come to one of the most quietly misunderstood ideas in all of gravity. The image of astronauts floating. We have all seen the pictures and the videos. People drifting through the cabins of spacecraft, turning slow somersaults in the air, pushing off walls with a single finger, and gliding across the room. Water floating in shimmering spheres, pens hovering in place, hair standing up in soft clouds around faces. And the phrase that almost always comes with these images is zero gravity. It sounds right. It sounds obvious. There is no up, no down, no weight, so there must be no gravity. The astronauts have left gravity behind. They have escaped it. They are floating because the pull of the Earth has gone away. This is the story we tell ourselves, and it is a story that makes a kind of surface sense. But it is not the real story. The real story is quieter and stranger, and in its own way, more restful. Let us begin with a simple fact. Astronauts on the International Space Station are not beyond the reach of Earth's gravity. They are not even close to being beyond it. The space station orbits at an altitude of about 250 miles above the surface of the Earth. That sounds high. It is high. It is far above the atmosphere, far above the clouds, far above any mountain. But from the point of view of gravity, 250 miles is almost nothing. The Earth is huge. Its gravitational pull reaches out much, much farther than that. At the altitude where the space station flies, the pull of Earth's gravity is still about 90% as strong as it is here on the ground. 90%. If you could stand on a platform at that height, without moving, without orbiting, just standing still on some imaginary tower, you would weigh almost the same as you do in your bed. You would not float. You would not drift. You would feel heavy, just as you do now. The gravity is still there, still pulling, still strong. So the floating is not about the absence of gravity. It is about something else entirely. What is really happening up there is that the space station and everything inside it is falling, continuously falling. Not falling straight down, not plummeting toward the ground, but falling in a very particular way. The station is falling around the Earth. It is moving sideways so fast that as it falls, the curve of the Earth drops away beneath it at the same rate. The station keeps falling toward the Earth, and the Earth keeps curving away, and so the station never hits the ground. It just keeps falling, endlessly, in a great smooth circle. This is what an orbit is. An orbit is not a place where gravity stops. An orbit is a state of continuous falling. The moon is falling around the Earth. The Earth is falling around the sun. The sun is falling around the center of the galaxy. Orbit after orbit after orbit, all of them the same basic motion, all of them a kind of falling that never reaches the ground. And this is the key to understanding the floating. The astronauts float because they are falling. They are falling at exactly the same rate as the spacecraft around them. Everything inside the station, the people, the equipment, the water, the air, the pens, the floating spheres of juice, all of it is falling together. And when everything falls together, when there is no difference in speed between you and the walls around you, you stop feeling your own weight. You become weightless relative to your surroundings. This state has a name. It is called free fall. Free fall means falling under the influence of gravity alone, with nothing pushing back against you. When you are in free fall, you feel no weight. Not because gravity has vanished, but because nothing is stopping your fall. The floor is not pushing up against your feet. The chair is not pressing against your back. Every part of you is accelerating at the same rate, under the same pull, and so there are no pressure points, no resistance, no sensation of weight. This is not just an idea. It is something you can imagine right here, without leaving your bed. Picture an elevator, a plain, ordinary elevator, the kind you might ride in a tall building. Now imagine that the cable holding the elevator snaps, and the elevator begins to fall. Inside the elevator, something strange would happen. The elevator car would fall, and the person inside would fall too. They would fall at the same rate. The person would no longer feel the floor pressing against their feet. If they held a small object in their hand and let go, the object would not drop to the floor. It would float, right where it was released, because both the object and the hand and the elevator are falling together. To the person inside, it would feel exactly as if gravity had been switched off. They would be weightless, floating, drifting, all while plummeting downward at tremendous speed. The falling would be real, the gravity would be real, but the experience inside the elevator would be identical to floating in deep space, far from any planet. This is the image that unlocks the whole puzzle. The astronauts on the space station are living inside a falling elevator. An elevator that is falling around the Earth instead of straight down, but falling nonetheless. The principle is exactly the same. The station and its contents are all in free fall together. The gravity is there, pulling strongly, but because everything is responding to that pull in exactly the same way, the relative experience is one of floating. No up, no down, no weight, just the gentle drift of objects moving together through space. Because of this, scientists and engineers tend not to use the phrase zero gravity when they are being precise. They say microgravity instead. The word micro means very small. And the reason they use that word is that the weightlessness on the space station is not quite perfect. There are tiny forces at play. The station is large enough that the pull of gravity is very slightly different at one end than the other. The station also experiences very slight drag from the uppermost traces of the atmosphere. The movements of astronauts inside the station create tiny vibrations. All these effects add up to a condition where the apparent gravity is not exactly zero, but something very, very close to it. A millionth of what we feel on the ground, or even less. So microgravity is the careful, accurate word. But the experience for the astronauts is the same. They float, they drift, they feel weightless. Not because gravity has gone away, but because they are in a continuous, unending fall. Now, you might wonder, if the astronauts are falling, why don't they feel the sensation of falling? Why isn't there that lurch in the stomach, that drop you feel on a roller coaster, or when a car goes over a hill? The answer takes us back to the idea from the last section, the idea about speed and acceleration. That lurch, that dropping feeling, comes from a change in speed, not from speed itself. On a roller coaster, you feel the drop because the car was being held up by the track, and then suddenly it is not. Your body was being supported, and then the support changes. There is a shift, a transition, a moment of acceleration from stillness into falling. That shift is what your inner ear detects. That is what makes your stomach feel like it is rising, but once you are in the fall, once the speed is steady and the acceleration is constant, the sensation fades. You settle into the fall. Your body accepts it. The inner ear fluid finds a new equilibrium, and the lurch goes away. The astronauts on the space station are not entering and leaving freefall in quick bursts. They are in freefall continuously. They have been in it since the moment the rockets shut off and the station settled into its orbit. There is no sudden drop, no jerking transition. They are just falling, smoothly, steadily, the way the Earth falls around the sun, the way the moon falls around the Earth. And so there is no lurch, no roller coaster stomach, just the calm, silent, steady state of falling that feels exactly like floating, exactly like stillness. The body adapts, the brain adapts. The sensation of falling becomes the new normal, and after a while, it stops feeling like falling at all. It just feels like being. This is a peaceful thing to contemplate. The astronauts up there, circling the planet every 90 minutes or so, are not straining against anything. They are not fighting. They are simply falling and floating and being carried by the same force that holds you gently against your mattress, the same gravity, the same pull. In your case, the fall is interrupted by the ground, by the floor, by the bed. That is why you feel weight. Weight is the sensation of something stopping your fall. In the case of the astronauts, nothing is stopping their fall. They are falling freely, and so they feel no weight. The difference between you and them is not the presence or absence of gravity. The difference is whether the fall is being stopped or not. You can feel a trace of this yourself, even lying here. When you are lying still, fully supported, your body is in its most restful relationship with gravity. You are not standing, so your muscles do not have to work to hold you upright. You are not walking, so your joints do not have to absorb the impact of your steps. You are fully stopped, fully supported, and the sensation is one of deep letting go. The astronauts in orbit have taken that letting go one step further. They have removed the support entirely, so that nothing presses back against them at all. But the underlying force, the pull that gives weight its meaning, is the same for you and for them. It is the same gravity, the same steady, patient attraction that has been with you since your first breath. And here is one more way to think about it, a way that often helps the idea settle into place. When you see those images of astronauts floating inside the space station, you are not watching people who have escaped gravity. You are watching people who have surrendered to it completely. They are not fighting it, they are not resisting it, they are letting gravity take them, fully, without any obstacle. And in that complete surrender they find weightlessness. There is something almost meditative in that. The idea that by stopping the struggle, by removing the resistance, what felt like a heavy burden becomes a state of floating. The gravity is still there. It has not diminished. It is just that the relationship has changed. The fall is now unbroken, the path is now clear, and so the weight disappears, not because the pull has weakened, but because it is no longer being opposed. As you lie here in the dark, you are somewhere on the spectrum between full weight and full weightlessness. You are not standing, so your muscles are relaxed. You are not sitting up, so your spine is not compressed. You are as close to free fall as a person on the ground can get, short of being in an airplane that flies in a special curved path to create brief periods of weightlessness for training. Your body is supported, yes, but the support is gentle, diffuse, spread across the whole surface of your back and legs and head. The pressure of the mattress is the only thing between you and the fall. If the mattress were to vanish, if the floor were to vanish, if the ground itself were to open up, you would begin to fall. And if you could fall freely, without air resistance, without anything in your way, you would feel what the astronauts feel. You would float. You would drift. You would be weightless. The gravity would still be there, pulling just as hard as ever, but you would no longer feel it as weight. You would feel it only as motion, as falling, as the quiet, endless, effortless arc of a body in free fall. So the next time you see a picture of an astronaut floating, you can let your mind drift to this understanding. They are not in a place without gravity. They are in a place without resistance. They are falling, and they are at peace with the fall. And you, lying here, are held in that same gravity, a little closer to the ground, a little more supported, but connected to the same force, the same pull, the same deep pattern that shapes everything from the smallest falling leaf to the largest orbiting galaxy. The astronauts float not because gravity is absent, but because they have let it carry them completely. And in that image, perhaps, there is a kind of invitation. An invitation to let go, just a little more. To sink into the support that is already there. To let gravity hold you, not as a burden, but as a steady, quiet presence that asks nothing of you except that you rest. That steady, quiet presence. It has been with us through every section so far. This idea of gravity as a pull, a mutual attraction between masses. Isaac Newton gave us this picture more than 300 years ago, and it is a picture that works. It worked for him, it worked for the astronomers who came after him, and it still works today for almost everything we do. When engineers plan the path of a spacecraft to Mars, they use Newton's equations. When architects calculate the load on a bridge, they use Newton's equations. When we predict the tides or the motion of the moon or the fall of an apple, we use Newton's equations. This description of gravity as a force that pulls on mass across distance is one of the most successful ideas in the history of human thought. It has been tested, checked, and confirmed in countless ways over centuries, and yet it is not the whole story. It is not the deepest story. There is another way to understand gravity, a way that came later, from a different mind, a different angle of approach, and that is where we are going now, very slowly, step by step. The mind was Albert Einstein's. The year was 1915, and the idea he put forward was not that Newton was wrong, but that Newton's picture was a kind of surface layer, and underneath it lay something stranger and more beautiful. Einstein suggested that gravity is not a force that pulls across space. Gravity, he said, is what happens when space itself is bent, or curved, by the presence of mass. Space and time, in his picture, are not an empty stage on which things happen. They are a kind of fabric, a seamless whole, and that fabric can stretch, and bend, and curve. When a massive object sits in that fabric, it makes a kind of dip, a hollow, and other objects move toward it, not because they are being pulled by a mysterious force, but because they are following the curve of the space around them. The mass tells space how to curve. The curved space tells mass how to move. That is the heart of Einstein's theory of gravity, which he called general relativity. Now, that is a lot to take in, and it is one of the more abstract ideas in this whole journey. So let us slow down and approach it from a different angle, an angle that uses a plain, everyday image. Imagine a large sheet, a bed sheet maybe, or a piece of rubber, stretched out flat and tight, held at all four corners. The sheet is smooth and even. If you place a small marble on it, the marble just sits there. If you give the marble a gentle push, it rolls in a straight line across the flat surface. Nothing surprising. Now imagine placing a heavy ball in the middle of the sheet, a bowling ball, perhaps, or a large rock. The weight of the ball presses down into the sheet, making a dip, a hollow, a curve. The sheet is no longer flat. It slopes down toward the heavy ball. Now, if you take that same small marble and place it near the edge of the sheet, it no longer sits still. It rolls inward, down the slope, toward the heavy ball. It looks as if the heavy ball is pulling the marble toward it, but nothing is pulling. The marble is just following the curve of the sheet. It is taking the easiest path through the shape that the heavy ball has created. This is the image that is often used to explain Einstein's idea, and it is a helpful image, as long as we remember that it is a simplified picture, not the literal truth. The sheet is not space, the bowling ball is not a planet, the marble is not a moon, but the image captures something essential. In Newton's picture, the bowling ball reaches out with an invisible hand and tugs on the marble across the empty space between them. In Einstein's picture, the bowling ball changes the shape of the space around it, and the marble simply moves through that changed space. There is no tug, there is no invisible hand, there is only the curve and the motion along the curve. Gravity, in this view, is not a force. It is geometry. It is the shape of the world. Let us sit with that for a moment. The shape of the world. When you feel gravity holding you to the bed, what you are actually feeling, in Einstein's view, is the curve of space and time around the Earth. The Earth is a massive object. It bends the fabric of space and time around it. And your body, moving through time, follows that bend. The bend leads toward the center of the Earth. The bed gets in the way. Your body presses into the mattress because the mattress is blocking your path along the curve. You are not being pulled down. You are being pushed up by the mattress, which is stopping you from following the natural curve of the space around you. This is a very different way of thinking about weight. It turns the whole picture upside down. In Newton's world, gravity reaches up from the Earth and pulls you down. In Einstein's world, the Earth curves the space around it, and the ground pushes up against you to stop you from sliding deeper into that curve. This is a hard idea to hold on to. It is abstract. It is not something you can see or touch directly. And that is okay. You do not need to grasp it fully for it to settle somewhere in the back of your mind. The important thing to carry forward is simply this. There are two ways to describe gravity. The first way, Newton's way, is to think of it as a force that pulls. The second way, Einstein's way, is to think of it as the bending or curving of space and time. Both descriptions are still used today. Both are correct within their own domains. Newton's description is simpler to calculate with, and for most everyday situations, from building bridges to launching rockets, it works beautifully. Einstein's description is more complete, and it is needed for situations where gravity is very strong or where extreme precision is required, like the orbits of satellites or the bending of starlight around the sun. Neither description is the absolute final truth. Both are models. Both are tools. And physicists use the tool that fits the job at hand. What made Einstein's picture so compelling was not just its elegance, though it is elegant in a deep mathematical way. It was that it made predictions that Newton's picture could not make, and those predictions turned out to be true. Einstein's curved space could explain a small wobble in the orbit of the planet Mercury that Newton's equations had never quite accounted for. Mercury is the closest planet to the Sun, deep in the curve of the Sun's gravity, and its orbit shifts very slightly over time, in a way that Newton's simple pull could not fully predict. Einstein's curved space predicted it perfectly. This was the first big test. There would be others, and we will come to them soon. But for now, the point is simply that the curved space picture is not just a story. It is a description that matches the real universe in measurable, testable ways. And yet, for all its power, the curved space picture does not replace the old pulling picture in your daily life. When you drop a spoon, you can still think of it as the earth pulling the spoon down. You will not be wrong. The spoon will fall. Newton's description will tell you exactly how fast it falls and how long it takes to hit the floor. Einstein's description will tell you the same thing, but with a much more complicated set of mathematical steps. For the spoon, the difference between the two descriptions is so tiny that no one would ever notice. The two pictures overlap almost perfectly in the weak gravity of everyday life. It is only in the strong gravity near a black hole, or in the precise timing of satellite signals, that the differences become important. So you do not have to choose between Newton and Einstein. You can hold both pictures loosely in your mind, and use whichever one helps you understand the moment. This is a gentle thing, really. The idea that two very different ways of seeing the same phenomenon can both be true. The universe does not demand that we pick one and discard the other. The universe just is, in all its complexity, and we build our models to fit the parts of it we can see and measure. Newton's model fits the falling spoon. Einstein's model fits the bending starlight. Both models describe the same gravity. Both are human creations, attempts to put words and numbers to something that may always remain, at some level, mysterious. And that mystery, that not quite knowing, is not a problem to be solved. It is just the way things are. It is the way things have always been, ever since people first looked up at the sky and wondered what held the moon in place. As you lie here in the dark, you can let your mind drift between these two pictures, not trying to resolve them, just letting them float side by side. In one picture, the earth is pulling on you, a steady, invisible force reaching up through the floor and the bed to tug on every atom of your body. In the other picture, the earth has curved the space around it, and you are sliding down that curve, and the bed is pushing back against you, and that push is what you feel as weight. Both pictures are beautiful in their own way. Both are true in their own domain, and both lead, eventually, to the same quiet conclusion. You are held. You are supported. The force, or the curve, or whatever name we give it, is steady and reliable, and asks nothing of you in return. It is simply there, as it has always been, as it will always be, the shape of the universe keeping you close to the ground. In the next part of our journey, we will go deeper into Einstein's picture, into the single insight that led him from the falling elevator to the curved space, the idea that falling and floating feel the same. That idea, simple as it sounds, is the key that unlocked everything else. But for now, just rest with the image of the sheet and the heavy ball, the curve and the marble. Let it be a soft image, a dreamlike image, something that drifts through your mind without needing to be pinned down. The universe is curved, in ways we can barely imagine, and you are moving along one of those curves, right now, held gently in the hollow made by the earth. That is enough. That is more than enough. That is the shape of things, quiet and deep, waiting for you to drift further into sleep. The shape of things, quiet and deep. That phrase settles into the dark like a stone dropping into still water, and from it, the next idea rises. The idea that led Einstein from the familiar world of falling apples and pulling forces into the strange world of curved space and bent time. It is an idea that sounds almost too simple at first, so simple that you might wonder why it took someone of Einstein's genius to see it clearly. But sometimes the deepest insights are the simplest ones, the ones hiding in plain sight, waiting for someone to notice them and take them seriously. This insight has a name. It is called the equivalence principle. The word equivalence just means two things that are equal, two things that cannot be told apart, two situations that feel exactly the same from the inside. And the equivalence that Einstein noticed, the one that started everything, is the equivalence between falling and floating, between the feeling of gravity pulling on you and the feeling of accelerating through space. He realized, in a flash of clarity that came to him years before the full theory was ready, that a person in a small, windowless room could not tell the difference between standing still on the surface of a planet and accelerating through empty space in a rocket. And similarly, a person falling freely in a gravitational field could not tell the difference between falling and simply floating in deep space, far from any source of gravity, with the gravity switched off. These two situations, being pulled by gravity and being accelerated by a rocket, feel identical from the inside. They are equivalent, and that equivalence, followed carefully to its logical end, led to the whole grand architecture of curved space and time. Let us slow down and walk through this thought experiment carefully, because it is one of the more abstract ideas in our journey, and it rewards patience. There are two parts to it, two imaginary rooms, two different situations, and we will take them one at a time. First, imagine a small room with no windows. It could be an elevator car, it could be a cabin, it could be a box floating somewhere in the universe. The important thing is that you cannot see outside. You are standing inside this room, and you feel the floor pressing up against your feet. You feel your own weight. If you hold a small object in your hand and release it, it drops to the floor. Everything feels normal. You would naturally assume that you are in a room that is standing still on the surface of a planet. Gravity is pulling you down. The floor is pushing back up. That is why you feel weight. That is why objects fall. That is the obvious explanation. But there is another possible explanation, and this is where the thought experiment gets interesting. Imagine that the room is not on a planet at all. Imagine that it is floating in deep space, far from any star or planet, in a place where gravity is effectively zero. Now imagine that the room is attached to a rocket, and the rocket is firing, pushing the room forward at a steady, constant acceleration. Inside the room, you would feel exactly the same thing as you felt on the planet. The floor would push up against your feet. A dropped object would fall to the floor. Your weight would feel normal. The acceleration of the rocket would create a sensation that is indistinguishable from gravity. The rocket is pushing the floor up against you, just as the ground pushes up against you on Earth. And because there are no windows, you have no way to know which situation you are in. Are you standing still in gravity, or are you accelerating through empty space? From inside the room, the two feel exactly the same. They are equivalent. This is the first half of the equivalence principle. Gravity and acceleration produce the same sensations. They are two sides of the same coin. If you are in that windowless room and you feel weight, you cannot say for certain whether that weight comes from the pull of a planet or the thrust of a rocket. The physics inside the room is identical in both cases. Every experiment you could perform inside that room would give the same results, whether the room sat on Earth or accelerated through deep space. A ball thrown in an arc would follow the same curve. A scale would register the same weight. Your own body would feel the same pressure on the soles of your feet. Now let us turn to the second half of the thought experiment. Imagine the same small, windowless room, but this time you are not standing on the floor. This time you are floating. You and the room, and everything in it, are drifting weightlessly. A pencil released from your hand stays where it is, hanging in the air. You feel no pressure on your feet. There is no up, no down. What situation are you in? Again, there are two possibilities. The first possibility is that you are in deep space, far from any planet or star, where gravity is so weak that you feel nothing. This is the obvious explanation. No gravity, no weight. Simple. But there is another possibility. You could be in a gravitational field, falling freely. You could be in an elevator whose cable has snapped, plummeting downward, accelerating under the pull of gravity. Or you could be in orbit around a planet, falling continuously around the curve of the world, as we discussed in the weightlessness section. In both cases, you and the room, and everything in it, are falling together under gravity. And because everything falls at the same rate, you feel weightless. You float. The pencil floats. There is no sensation of falling because nothing is pushing back against you. From inside the room, with no windows, you cannot tell whether you are floating in deep space with no gravity or falling freely in a strong gravitational field. The two situations feel exactly the same. They are equivalent. This is the second half of the equivalence principle. Free fall and the absence of gravity are indistinguishable from the inside. A floating astronaut in a falling elevator has no way to know, without looking outside, whether gravity has been switched off or whether they are simply falling under its influence. The experience is identical, the physics is identical, the body cannot tell the difference. Now you might ask, why does this matter? Why was this simple observation, that falling feels like floating and gravity feels like acceleration, so important? The answer is that it gave Einstein the clue he needed to rethink gravity entirely. If gravity and acceleration are equivalent, then the laws of physics must work the same way in both situations. And if acceleration can be described in terms of curved paths through space and time, then gravity might also be described in terms of curved space and time. The equivalence was the seed from which the whole tree of general relativity grew. Let us try to feel this connection, even if we cannot follow the mathematics all the way to the end. When a rocket accelerates through space, it is changing its motion. It is moving faster and faster. In the language of physics, it is undergoing constant acceleration, and the people inside feel that acceleration as a force, a push, a simulated gravity. Now, if acceleration feels like gravity and gravity feels like acceleration, then maybe what we call gravity is not a force at all. Maybe it is just what acceleration feels like when you are standing on the surface of a planet. Maybe the ground is pushing up against you, accelerating you away from your natural free-fall path through curved space, and that push is what you feel as weight. The Earth curves the space around it. Your body wants to fall along that curve, toward the center of the Earth, but the ground gets in the way. The ground pushes up against you, accelerating you away from that natural path, and that upward push, that acceleration away from freefall, is what you feel as gravity. It is not a pull down. It is a push-up. The equivalence principle is what allowed Einstein to see weight in this new, inverted way. This is a deeply counterintuitive idea. Our whole lives, we have felt gravity as a downward pull. It is built into our bones, our language, our instincts. To think of it instead as an upward push, as acceleration away from a curved path, requires a kind of mental flip. And it is okay if that flip does not happen all at once. It is okay if the idea just hovers at the edge of your awareness, half understood, like a dream you are not quite sure you had. The important thing is not to master it, but to let it be there, gently, as part of the larger picture. The equivalence between gravity and acceleration is the reason Einstein started thinking about curved space. It is the reason we have a theory of gravity that can describe black holes and the bending of starlight and the slowing of time. It is the quiet, logical step that opened the door to a new universe. And there is something else here, something that connects back to the very beginning of our journey. The equivalence principle means that your experience of gravity is not unique to being on a planet. An alien civilization living on a vast space station, spinning to create artificial gravity through acceleration, would feel the same weight, the same pull, the same sensation of standing, the same fall of a dropped object. They might never have seen a planet. They might live their whole lives in space. But their experience of gravity would be the same as yours. The physics does not care whether the weight comes from a mass curving space or from a rocket firing in deep space. It feels the same. It is the same. That is the deep meaning of equivalence. It ties together situations that look completely different from the outside and shows they are identical from the inside. So as you lie here in the dark, feeling the weight of your body in the bed, you can try on this new way of thinking. You are not being pulled down. You are being pushed up. The bed, the floor, the ground, the whole solid earth, is pushing up against you, accelerating you away from the curved path you would naturally follow if nothing were in the way. You are in a constant state of gentle upward acceleration, just enough to keep you from falling freely through the curve of space around the planet. That push is what you feel as weight. And if the bed were to vanish, if the floor were to vanish, if the ground were to open up, you would enter free fall. You would float. You would feel weightless. Not because gravity had disappeared, but because the upward push had stopped. You would be following your natural path through curved space at last, and that path would feel exactly like floating in the deep emptiness between the stars. This is the insight that Einstein carried with him as he worked, over years of patient, difficult thought, toward the full theory of general relativity. The equivalence principle was the guiding light. It told him that gravity and acceleration are two expressions of the same underlying thing. And if acceleration is about motion through space and time, then gravity must also be about motion through space and time. Specifically, it must be about the curvature of space and time around mass, the heavy ball on the stretched sheet, the marble rolling down the slope, the curve that looks like a pull but is really just the shape of the world. We are going to leave this idea here, letting it rest, not forcing it to resolve. The equivalence principle is one of those ideas that deepens with time. The more you sit with it, the more it quietly rearranges the furniture of your mind. You do not need to do anything with it tonight. You do not need to test yourself on it or explain it to anyone. It is enough that it has been spoken, that it has entered the quiet space of this room, that it is floating somewhere in the dark near you. The falling elevator and the rocket in deep space, the floating room and the planet's surface. These images can drift together, merging and separating, like clouds in a night sky. And through them, the deeper shape of gravity begins to show itself. Not as a simple pull, not as a force like any other, but as something woven into the very structure of space and time, something that reveals itself through the simple fact that falling and floating feel the same. Something woven into the very structure of space and time. That is not just a poetic phrase. It is a literal description of what Einstein's theory tells us. And if gravity really is the shape of space and time, then we should be able to see its effects on things that travel through that space and time. Light, for instance, and time itself. These are the two strangest and most well-tested consequences of the curved universe. Gravity, because it bends space and time, bends the path of light, and gravity, because it bends space and time, also slows down the passage of time. These are not metaphors. They are real, measurable effects. They have been tested, they have been confirmed, and they are happening in tiny ways all around you, right now, as you lie still in the dark. Let us start with light. Light travels through space. That is something we all know. A beam of light moves in a straight line unless something gets in its way. A mirror can bounce it, a lens can bend it, but in empty space, with nothing blocking it, light goes straight. That was the assumption for centuries. It is built into the way we talk about light. We say things like straight as an arrow or straight as a beam of light. Straightness is part of the essence of light. But Einstein's curved space changed that. If space itself is curved, then a straight line through that space is not necessarily straight in the way we normally think of it. The light is still taking the straightest possible path. It is not deviating. It is not being pulled. It is simply following the curve of the space it is moving through. If the space is bent, the path of the light bends with it. So a beam of starlight passing near a massive object, like the sun, should bend slightly as it goes by. The light is not being attracted by the sun's gravity. The light is moving through space that the sun has curved, and the curve shapes the path. This was one of the first predictions Einstein made with his new theory. If the sun curves the space around it, then starlight passing close to the sun should bend by a tiny amount. The stars near the edge of the sun, during a total solar eclipse when the sun's bright face is blocked by the moon, should appear to be slightly shifted from their normal positions. The light from those stars, traveling through the curved space near the sun, would follow the curve, and by the time it reached telescopes on Earth, it would be coming from a slightly different direction than it would if the sun were not there. The stars would seem to have moved, just a little, just for the duration of the eclipse. This prediction was tested. In 1919, a British astronomer named Arthur Eddington led a team to observe a total solar eclipse. The eclipse was visible from the island of Principe, off the coast of West Africa, and from parts of Brazil. Eddington's team took photographs of the stars near the sun during the eclipse. They measured the positions of those stars very carefully, and then, months later, they compared those photographs to photographs of the same patch of sky taken at night, when the sun was not there. The stars that had appeared near the sun during the eclipse were, in fact, shifted. Their light had bent. The amount of bending matched what Einstein's theory predicted. Newton's theory, if you tried to use it to predict the bending of light, gave a different number, half as large. The eclipse observations matched Einstein, not Newton. This was the moment that general relativity moved from being a beautiful theory to being a confirmed description of the real universe. The bending of starlight was real. Space really was curved around mass. Light really did follow that curve. Let that image settle for a moment. The light of a distant star, traveling across the vast emptiness of space for years or centuries or millennia, arrives at our solar system, and as it passes near the sun, the very space it is traveling through is gently warped, gently bent, by the mass of the sun. The light follows the warp. It comes out the other side at a slightly different angle, and we, on Earth, see the star in a slightly different place than it really is. Not because the star moved, not because the light was pulled by a force, but because the road the light was traveling on curved. The road itself, the space itself. That is what gravity does, in Einstein's picture. It curves the road. Now let us turn to the second strange consequence, the one that has to do with time. Gravity slows time. This effect has a name, gravitational time dilation, but as always, we will describe it in plain words before we name it. The idea is this: the closer you are to a massive object, the more slowly time passes for you. Not just the ticking of a clock, not just the swinging of a pendulum. Time itself, the fundamental pace at which events unfold, is slower deep in a gravitational field than it is far away. A clock on the surface of the Earth runs very slightly slower than a clock on a satellite orbiting high above. A clock on the surface of the sun would run slower still, and a clock near a black hole, in the most extreme case we know of, would slow almost to a stop as seen by an observer far away. This is not a mechanical problem. It is not that gravity interferes with the gears or the electronics. It is that time itself flows at different rates depending on how curved the space around you is. The deeper you are in the gravitational curve, the slower time goes. This is a direct consequence of the curved space and time that Einstein described. Mass curves not just space, but time as well. And the curve in time shows up as a change in the rate at which time passes. It is as if the presence of mass stretches time, slows it down, makes each second last a little longer than it would in empty space. This is a deeply strange idea. It is not something we ever notice in daily life. The differences are far too small. Over your entire lifetime, the time you have spent on the surface of the Earth has passed maybe a fraction of a second slower than it would have passed if you had spent your whole life floating in deep space. A fraction of a second, you cannot feel it. No watch you could buy would measure it, but it is real. It has been measured, and it is measured every single day by the satellites that make up the global positioning system, the GPS network that your phone uses to know where you are. GPS satellites orbit the Earth at an altitude of about 12,500 miles. That is much higher than the space station. At that altitude, they are far enough from the Earth that the gravitational time dilation is noticeable. The clocks on those satellites run slightly faster than clocks on the ground, because they are higher up in the gravitational field, in less curved space. The difference is tiny. It is measured in nanoseconds, billionths of a second, but GPS works by timing signals very precisely. A signal from a satellite travels at the speed of light, and light covers about 1 foot in 1 nanosecond. So if the timing is off by even a few nanoseconds, the position calculation is off by several feet. Over the course of a day, if the time difference were not corrected, the GPS positions would drift further and further from the truth, becoming useless after just a few minutes. So the system is built to correct for this. The satellites adjust their clocks to account for the faster passage of time at their altitude. They are programmed with Einstein's equations. Every time you open a map on your phone and see a blue dot showing you where you are using technology that has been corrected for the curvature of time around the Earth. The bending of time is not a distant theory. It is part of the invisible infrastructure of the modern world. There is a quiet symmetry here. Gravity bends space, and that bending shows up in the path of light. Gravity bends time, and that bending shows up in the ticking of clocks. Both effects are real. Both have been tested. Both are part of the same underlying truth. Mass curves the fabric of space and time around it. Light follows the curve, and time flows along the curve. And everywhere in the universe, from the smallest pebble to the largest galaxy, these curves are present, shaping the motion of everything. You can think of it like this, if it helps. Imagine a slow river moving through a wide valley. The water flows at a certain speed. Now imagine the river narrows, and the valley floor drops. The water speeds up in some places and slows down in others, following the shape of the land. Space and time are like that river. They flow. They have a shape. And mass is like the shape of the land that the river moves through. A planet, a star, a black hole. These are deep places in the landscape. The river of time flows more slowly through the deep places. The river of space bends as it moves around them. Light and matter, and even the passage of moments all follow the shape of the land. That is gravity, not a force that pulls the river, the shape of the valley itself. And here, lying in your bed, you are in one of those deep places, not the deepest, not by far. The Earth's gravity is gentle compared to a star, gentle compared to a black hole. But it is deep enough that time is passing very slightly more slowly for you than it is for a satellite overhead. Very slightly, immeasurably slightly, but the effect is there. The mass of the Earth has curved the space and time in this room, and your body is resting inside that curve. Your clock is ticking a tiny bit slower than a clock in orbit. Your light, if you turned on a lamp, would bend by an amount too small to ever notice. But it would bend. The curved universe is not somewhere else. It is here. It is now. It is under the bed, inside the blankets, woven through the air. You are living inside Einstein's gravity, just as much as you are living inside Newton's. There is no need to hold on to the numbers. The numbers are not the point. The point is the idea, the gentle, strange, true idea that gravity reaches into the very flow of time and the very path of light. That the solid ground under you is not just a surface, but a kind of dimple in the fabric of reality, a place where the universe bends a little, and that bend is what you feel as weight. That the starlight arriving from distant suns has been shaped by every curve it passed along the way. That the blue dot on your phone's map is a quiet, everyday proof that time flows differently at different heights. These are not things you need to understand in detail. They are things you can let wash over you, like warm water, like soft music, like the slow drift of clouds across a dark sky. And as we prepare to move forward, we are going to leave the deep strangeness of curved time and bent light behind and return to something more familiar, something rhythmic and steady and close to home. We are going to talk about the tides, the slow breathing of the ocean, the pull of the moon. Because gravity, for all its abstract strangeness, is also the force that moves the sea. It is both the most cosmic and the most earthly thing. It bends starlight and it lifts the water. It slows time and it pulls the tides. And that is what we will explore next, as we drift further into the quiet of the night. And so we return to something familiar, something rhythmic, something that has been part of the earth for as long as there have been oceans and a moon. The tides, the slow, steady rise and fall of the sea. Twice a day, in most places along the coast, the water comes in and then goes out again. It breathes. It pulses. It is one of the most reliable rhythms on the planet, and it is driven entirely by gravity. The tides are gravity made visible, made tangible, made into motion that you can watch from a shore or hear from a seaside window. And they are also a beautiful example of how gravity works in a subtle, differential way. Not just pulling evenly on everything, but pulling slightly more on what is closer and slightly less on what is farther away. That difference is the key to the tides. Let us begin with the moon. The moon is the main driver of the tides. It orbits the Earth at a distance of about 240,000 miles, and it pulls on the Earth with its gravity. But the pull is not the same everywhere on the planet. The side of the Earth that faces the moon is closer to the moon, so it feels a stronger pull. The center of the Earth feels a medium pull. The far side of the Earth, the side facing away from the moon, feels a weaker pull because it is farther away. This difference in the strength of the pull across the body of the Earth is what creates the tides. Scientists sometimes call this a differential force, meaning a force that varies, that is different at different points. But you do not need to remember that term. You just need the image. The moon is tugging on the Earth unevenly. The near side gets tugged the most. The far side gets tugged the least. And that uneven tug stretches the Earth slightly. The solid Earth is too rigid to stretch much, though it does stretch a tiny bit, a few centimeters, which is measurable with sensitive instruments. But the oceans are fluid. They can move. They can flow. And so they respond to this uneven pull by bulging outward. On the side of the Earth facing the moon, the ocean bulges toward the moon, pulled by the stronger gravity. On the opposite side of the Earth, the far side, the ocean also bulges outward, but for a slightly different reason. The moon's pull on the far side is weaker, so the water there is not held as tightly toward the moon as the rest of the Earth. The solid Earth is pulled away from the far side water, in effect leaving a bulge behind. So there are two bulges, one facing the moon and one facing away. Two high points in the global ocean, sitting on opposite sides of the planet. Now, the Earth spins. It rotates on its axis once every 24 hours. As it spins, it carries the continents and the coastlines through these two bulges. When a coastline passes into one of the bulges, the water level rises. That is high tide. When the coastline passes out of the bulge, the water level falls. That is low tide. Because there are two bulges, most coastlines experience two high tides and two low tides each day. The timing shifts by about 50 minutes from one day to the next, because the moon is also moving in its orbit. The moon takes about 24 hours and 50 minutes to return to the same position in the sky, so the whole tidal cycle shifts later by about 50 minutes each day. It is a gentle, predictable, endlessly repeating pattern, driven by the mutual pull between the Earth and the moon, and by the fact that the pull is not quite the same strength everywhere. This is the simple picture. The moon creates two bulges. The Earth spins through them. The tides rise and fall. But the real tides are more complicated than this simple picture, because the oceans are not a uniform blanket of water covering a smooth globe. The continents get in the way. The shape of the seafloor matters. The water sloshes around in ocean basins, bouncing off coastlines, creating complex patterns. In some places, the tides are huge. In the Bay of Fundy, on the coast of Canada, the difference between high and low tide can be more than 50 feet. In other places, the tides are almost invisible. Some coastlines get only one high tide a day instead of two, because of the shape of the local ocean basin. The details are messy and local, but the driving force is the same everywhere. The moon pulls unevenly on the Earth and the ocean responds. And the moon is not the only body that pulls on the Earth's oceans. The sun does too. The sun is enormously more massive than the moon, but it is also much, much farther away. Because the sun is so far, the difference in its gravitational pull between the near side and the far side of the Earth is smaller than the moon's difference, even though the sun's total pull on Earth is much stronger. The differential effect, the stretching effect, is what matters for tides, not the total strength of the pull. So the sun's tidal effect is about half as strong as the moon's. The sun contributes its own smaller bulges to the ocean, and these solar bulges combine with the lunar bulges in interesting ways. When the sun and the moon are lined up with the Earth, which happens during a new moon and a full moon, their tidal effects add together. The high tides are higher than usual, and the low tides are lower than usual. These are called spring tides, though the name has nothing to do with the season of spring. It comes from an old word for a rising or swelling. Spring tides happen roughly every 2 weeks, when the sun and the moon are at right angles to each other, as seen from Earth, which happens during the first and third quarters of the moon. Their tidal effects partially cancel. The high tides are lower than usual, and the low tides are higher than usual. These are called neap tides. The cycle from spring tide to neap tide and back again is another rhythm, a slower one, layered on top of the daily rise and fall. So the ocean is never truly still. It is always moving, always responding, always being pulled and released by the moon and the sun. You can think of it as the ocean breathing. Inhale, and the water rises up the shore. Exhale, and the water recedes. Twice a day, every day, without fail, for billions of years. The tides were rising and falling long before there was any life on land to see them. They rose and fell while the first fish crawled out of the sea. They rose and fell while the dinosaurs walked the earth. They rose and fell while the first humans built their first villages by the shore. They are rising and falling right now, somewhere in the world, as you lie here in the dark. The same gravity that holds you to the bed is lifting the ocean, right now, somewhere under the moon. There is something deeply restful about the tides. They are a reminder that gravity is not just an abstract concept, not just a set of equations, not just a bending of space and time that takes a physicist to understand. Gravity is also the force that moves the water. It is the force that you can hear if you sit by the shore on a quiet night, the slow wash of the waves, the gentle hiss of the tide coming in. The water is answering the moon. It has been answering for billions of years, and the moon is slowly, very slowly, moving away from the Earth as a result. The tides create friction, and that friction transfers a tiny bit of energy from the Earth's spin to the moon's orbit, pushing the moon about 1.5 inches farther away each year. This is a real effect, measured by lasers bounced off mirrors left on the lunar surface by the Apollo astronauts. The moon is drifting away, very gradually, and the Earth's day is getting very gradually longer as the spin slows down. Billions of years ago, a day on Earth was only about 6 hours long, and the moon was much closer. Billions of years from now, the day will be much longer, and the moon will be much farther away. The tides are a snapshot in a very long, slow dance. But for now, for tonight, the rhythm is steady. The tides rise and fall. The moon keeps its patient watch. The sun adds its quieter contribution. And somewhere, on a coastline you may have visited once or may visit someday, the water is creeping up the sand, then turning, then flowing back out to sea. In and out, like breathing, like the slow rhythm of your own chest rising and falling under the blankets. There is a connection there, a quiet parallel. The same force that moves the ocean is the force that keeps you here, settled, supported, at rest. The tides are gravity's most visible heartbeat, the pulse of the planet's water, driven by the patient pull of a small world 250,000 miles away. As you settle deeper into the bed, you can let your mind drift to that image, the ocean under the moon, the water lifting, almost imperceptibly, across thousands of miles of sea, the coastline receiving the tide, the waves spreading up the shore, then drawing back again. The moon overhead, silent and bright, pulling on the water, pulling on you, pulling on everything. The sun on the other side of the planet, adding its own gentler pull, and the whole system, Earth and moon and sun, held together by the same force, moving in the same quiet dance. The tides are just one expression of that dance, one way that gravity shows itself in the world. And as you breathe in and breathe out, you are keeping time with the ocean, whether you know it or not. The rhythm is the same, the pull is the same, the stillness and the motion folded together like the rise and fall of the sea. The stillness and the motion folded together. That phrase could serve as a gentle introduction to the next place we are going, a place where gravity reaches its most extreme expression, a place where stillness and motion become almost the same thing, where the curve of space becomes so deep that it folds inward on itself. We are going to talk about black holes. The name itself can sound dramatic, can conjure images of cosmic whirlpools and things being sucked into darkness. But we are not going to approach it that way. We are going to approach it calmly, slowly, the way we have approached everything else. A black hole is not a monster. It is not a threat. It is simply a region of space where gravity has become, in a very literal sense, overwhelming. It is what happens when mass is packed so densely, so tightly, that the curvature of space and time around it becomes extreme. There is no need for drama. There is only physics, and the quiet acceptance of what the physics tells us. Let us begin with the most plain, everyday definition. A black hole is a region of space where the pull of gravity is so strong that nothing, not even light, can escape from it. That is the core idea. Everything we have talked about so far, the mutual pull, the curved space, the bending of light, the slowing of time, all of it comes together in a black hole and is pushed to its limit. If you take enough mass and squeeze it into a small enough space, the gravity at the surface becomes so intense that the escape speed, the speed you would need to leave the surface and fly away, becomes greater than the speed of light. And since nothing can travel faster than light, nothing can leave. Not a rock, not a spaceship, not a beam of light. Everything that crosses a certain threshold is bound there, forever, as far as we understand. That threshold has a name, but let us describe it in plain words first. Imagine you are drifting through space, far from any star, and you are approaching a black hole. At first, you would not see anything unusual. The black hole itself does not glow. It does not shine. You might see the light from distant stars bending around it, distorted by the curved space, but the hole itself would be dark. As you got closer, the gravity would grow stronger. There would come a point, a boundary, a kind of invisible surface in space, where the gravity becomes exactly strong enough that even light cannot climb back out. That boundary is the point of no return. Once you cross it, there is no coming back. Not because you would be destroyed, necessarily, but because every possible path, every direction you could turn, every move you could make, leads only inward, toward the center. The geometry of space and time becomes so bent that all roads lead down. This boundary is called the event horizon. The word event horizon, when you break it down, simply means the edge beyond which events, things that happen, can no longer be seen from the outside. It is the horizon of the black hole, the line that separates the region from which light can still escape from the region where it cannot. The event horizon is not a physical wall. It is not a solid surface. If you were falling into a black hole, you would not feel yourself pass through it. There would be no bump, no jolt, no signpost telling you that you had crossed the line. The gravity at the event horizon might be very strong, but your body would not necessarily feel anything unusual at that exact moment, because every part of you would be falling together. The danger, if we can call it that, would come from the fact that the gravity changes very rapidly near a black hole. The pull on your feet would be significantly stronger than the pull on your head, and your body would be stretched, very gently at first, and then more intensely, into a long, thin shape. Physicists sometimes call this spaghettification, though the word is a little playful for such a serious process. The point is simply that the difference in gravity across a small distance becomes enormous near a black hole. It is the same tidal effect that moves the oceans, but concentrated, intensified, until it can pull apart even the densest objects. But we are not here to dwell on falling into black holes. We are here to understand what they are, calmly, from a distance. A black hole is what remains after a very massive star runs out of fuel and collapses. Stars are held up by the energy released in their cores, energy that pushes outward against the inward pull of gravity. When a star much more massive than our Sun exhausts its fuel, the outward push stops, and gravity takes over completely. The core of the star collapses inward, crushing itself into a smaller and smaller volume. If the core is massive enough, nothing can stop the collapse. The matter keeps falling inward until it reaches a point where the density, the amount of mass packed into a given space, becomes effectively infinite. The entire mass of the star's core is compressed into an unimaginably small point. That point, the place where all the mass ends up, is called the singularity. And it is here that our understanding genuinely stops. The singularity is a word that physicists use to mark the edge of what they know. At the singularity, according to the equations of general relativity, the curvature of space and time becomes infinite. The density becomes infinite. The equations themselves break down. They stop giving meaningful answers. This does not necessarily mean that a singularity literally exists as a point of infinite density inside a black hole. It means that our current theory, general relativity, cannot tell us what happens there. The theory has reached its limit. To understand the center of a black hole, we would need a theory that combines gravity with quantum mechanics, the physics of the very small. And that theory, as we will discuss later, does not yet exist. So the honest answer to the question of what happens at the very center of a black hole is that nobody knows. Physicists are open about this gap. It is not hidden, it is not glossed over. It is simply one of the places where our knowledge runs out, and the not knowing is part of the landscape. This is important to sit with for a moment. Black holes are often described in ways that make them sound fully understood, as if science has everything figured out. But the truth is more modest. We understand the outside of a black hole, the event horizon, the curved space around it, the effects it has on nearby matter and light. These things are described very well by general relativity. We have evidence that black holes exist. We have seen their effects on the orbits of stars near the center of our galaxy. We have detected the ripples in space, called gravitational waves, that are produced when two black holes spiral together and merge. And in 2019, we saw the first direct image of a black hole's shadow. This was a major achievement, and it is worth describing quietly, without fanfare. The Event Horizon Telescope is not a single telescope. It is a network of radio telescopes spread across the entire Earth, working together to create a virtual telescope the size of the planet itself. This network pointed its attention at the center of a galaxy called Messier 87, a huge elliptical galaxy about 55 million light-years away. At the center of that galaxy is a black hole with a mass of about 6.5 billion times the mass of our Sun. The telescope network captured an image of the hot, glowing gas swirling around the black hole. In the center of that glow was a dark region, a shadow. That shadow is the black hole's event horizon, the place where light cannot escape. The image is not a photograph in the ordinary sense. It is a reconstruction from radio waves, assembled by combining data from telescopes all over the world. But it is a real image of a real black hole. It matches what general relativity predicted. The shadow is the right size. The ring of light around it is bent by the black hole's gravity, just as Einstein's theory said it would be. It was a quiet confirmation, a moment of alignment between theory and observation, that deepened our confidence that black holes are real, and that we understand, at least in broad outline, how they work. But the image only shows us the event horizon and the region just outside it. It does not show us the singularity. It cannot. The singularity is hidden behind the event horizon, inaccessible to any observation from the outside. This is sometimes called the cosmic censorship hypothesis, the idea that the universe somehow protects us from ever seeing a naked singularity. Whether this hypothesis is always true is another open question, but for the black holes we know about, the event horizon does indeed shield the center from view. The singularity remains a mystery, a place where the known laws of physics fall silent. So a black hole is both a triumph and a humbling. It is a triumph of general relativity, which predicted its existence and describes its outer structure with remarkable precision. And it is a humbling, because it contains within it a place where our best theory breaks down and tells us, very clearly, that there is more to learn. This combination of knowing and not knowing is not something to be frustrated by. It is the natural state of science. Every answer opens new questions. Every theory has edges. And black holes are one of those edges, a place where the familiar gives way to the unknown, and the unknown is allowed to sit, quietly, without being forced into a premature answer. As you lie here in the dark, a black hole is not something to be afraid of. It is something to be curious about, in a soft, distant way. The nearest known black hole is thousands of light years away. They are not lurking in the solar system. They are not going to pull the Earth out of its orbit. They are just out there, in the vast spaces between the stars, doing what gravity does when mass is pushed to its extreme. They are the deepest curves in the fabric of space and time, the places where the river of time flows so slowly that it almost stops, as seen from far away. They are the places where light makes its final, endless journey around the drain of curved space before crossing the horizon and falling inward. They are, in a strange way, the most peaceful places in the universe, because nothing that enters them ever returns. All struggles end, all journeys stop, the fall becomes eternal. And maybe there is something restful in that image, a place where gravity is so strong that it holds everything, forever, in a silent, unbreakable embrace, a place where time, for the falling observer, continues normally, but for the outside universe, slows and fades and eventually, at the horizon, seems to freeze. The black hole is the ultimate expression of the force we have been tracing all night. It is gravity, not as a gentle pull, not as a subtle curve, but as the dominant fact of existence, shaping everything, bending everything, holding everything. And yet, even in its extremeness, it is the same gravity that holds you now, the same physics, the same equations, the same quiet, patient presence, just concentrated to a degree that is hard for the mind to fully grasp. Let that image drift for a while. The dark shadow at the center of a distant galaxy, the ring of bent light, the silent horizon, the unknown center, all of it held in the same fabric of space and time that you are resting in right now. The same gravity, the same pull, the same deep pattern, from the smallest falling leaf to the largest black hole. It is all one story, and we are going to continue that story as we move into the next part, where we sit with the things we do not yet know, the open questions, the gaps in the picture, because gravity, for all its familiarity, still holds mysteries that no one has solved. And that too is part of the calm, that too is part of the dark, and that too is part of the dark, the not knowing, the open questions, the places where the trail of understanding goes cold, and the landscape of the unknown opens up before us. We have spent much of this journey building a picture of gravity, layering idea upon idea, from the falling apple to the bending of starlight, to the silent horizon of a black hole. And along the way, we have touched on the fact that some things about gravity remain puzzling. Now we are going to sit with those puzzles directly, not to solve them, not to pretend they are smaller than they are, but to let them be what they are, which is genuine mysteries at the heart of physics. This is the section where we allow the not knowing to take center stage, calmly, without any rush to fill the silence. Let us begin with the simplest and most striking of the puzzles. Gravity is extraordinarily weak. We said this all the way back in the opening section, and it has been a quiet thread running through everything since. Of the four fundamental forces that physicists have identified, gravity is by far the weakest. The strong nuclear force, which holds the centers of atoms together, is something like 10 to the 38th power times stronger than gravity. That is a number so large it has no name. It is a 1 followed by 38 zeros. Electromagnetism, the force that governs light and electricity and the structure of atoms, is also vastly stronger than gravity. A small refrigerator magnet can hold a paperclip against the floor, and in doing so, the electromagnetic force in that tiny magnet is overcoming the gravitational pull of the entire Earth. The weak nuclear force, which plays a role in certain kinds of radioactive decay, is also, despite its name, far stronger than gravity. Gravity is the odd one out. It is the featherweight in a ring of heavyweights, and nobody knows why. This is not a small puzzle. It is one of the great open questions in physics, and it has a name, the hierarchy problem. The word hierarchy just means a ranking, an ordering. The problem is that the ranking of the forces makes no obvious sense. Why should gravity be so much weaker than everything else? Why should there be such an enormous gap between the force we feel most directly in our bodies and the forces that shape the invisible world of atoms and particles? There are ideas, of course. Physicists have proposed possible explanations. Some involve extra dimensions of space, dimensions that we cannot see, into which gravity leaks away, making it seem weaker in our three-dimensional world. Others involve new particles or new symmetries of nature, but none of these ideas has been confirmed by experiment. The hierarchy problem remains an open question, a place where our current understanding simply does not reach. It is a crack in the foundation, and nobody knows what lies beneath it. This weakness of gravity is connected to another deep puzzle, which is that gravity does not fit with the other great pillar of modern physics, quantum mechanics. Quantum mechanics is the physics of the very small. It describes the behavior of atoms and particles with extraordinary precision. It has been tested in countless experiments and has never been found wrong. It is the basis for much of modern technology, from computer chips to lasers to medical imaging. But quantum mechanics, for all its power, does not include gravity, and general relativity, for all its power, does not include quantum mechanics. The two great theories of modern physics, the theory of the very large and the theory of the very small, do not speak the same language. They are like two magnificent maps of the same territory, drawn in different scales and different symbols, and where they overlap, in places like the center of a black hole or the first moment of the universe, the maps contradict each other. Physicists have been trying to build a bridge between these two theories for nearly a century. The hoped-for bridge has a name: quantum gravity. A theory of quantum gravity would describe gravity in the language of quantum mechanics as a force carried by tiny particles, in the same way that electromagnetism is carried by particles called photons. The hypothetical particle that would carry gravity is sometimes called the graviton. But the graviton has never been detected, and the mathematics of quantum gravity has proven to be very difficult. The straightforward approach, treating gravity like the other forces and trying to apply the same quantum rules, leads to equations that produce nonsense, infinities that cannot be removed. Something deeper is needed, something we have not yet found. There are candidates for a theory of quantum gravity. The most famous is string theory, the idea that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings of energy. In string theory, the different particles and forces arise from different modes of vibration of these strings, and gravity emerges naturally as one of them. String theory is a beautiful and mathematically rich framework, and it has generated a great deal of insight over the decades. But it has not yet made a prediction that can be tested by experiment. The strings, if they exist, are far too small to be seen by any instrument we can currently build, and so string theory remains, for now, a kind of mathematical dream, a possible answer that has not yet been confirmed or refuted. Another candidate is loop quantum gravity, which takes a different approach. Instead of adding extra dimensions or tiny strings, it tries to quantize space and time themselves, to build the fabric of the universe out of tiny, discrete loops. In this picture, space is not a smooth, continuous sheet, but a kind of network, a weave of extremely small units, like the pixels on a screen. Loop quantum gravity makes some tentative predictions, but like string theory, it has not yet been tested by experiment. The energies and scales at which quantum gravity effects become important are so extreme, so far beyond what we can produce in a laboratory, that direct tests remain out of reach for the foreseeable future. So we are left with a gap between the two great descriptions of the physical world. General relativity on one side, flawless in its domain. Quantum mechanics on the other, flawless in its domain. And no working bridge between them. This is not a failure of science. It is a signpost, pointing toward a deeper level of understanding that we have not yet reached. It is the recognition that our current knowledge is incomplete, and that there is more to learn. The not knowing here is not a source of frustration. It is a source of quiet anticipation. It is the open door at the end of the hallway. It is the dark room that has not yet been lit. And there is more. Even without venturing into the extremes of black holes or the Big Bang, even in the everyday universe, there are things that gravity tells us that we do not understand. The motions of galaxies do not make sense if we only count the mass we can see. The stars at the edges of spiral galaxies orbit too fast. The galaxies in clusters move too quickly. The light from distant galaxies bends more than it should. All of these observations point to the same conclusion. There is more gravity out there than the visible matter alone can account for. There is something else, something that has mass and pulls on other things gravitationally, but does not emit light, does not absorb light, does not interact with light in any way. It is invisible. It is transparent. It is, as far as we can tell, completely dark. This unknown something has a name. It is called dark matter. Dark matter is not a thing that has been seen directly. It is a placeholder, a name for a set of gravitational effects that we cannot otherwise explain. We infer its presence from the way galaxies rotate, from the way light bends around galaxy clusters, from the way the large-scale structure of the universe has formed over billions of years. Something is providing extra gravity. Something is shaping the cosmos. And that something, whatever it is, appears to be about 5 times more abundant in the universe than all the ordinary matter we can see, the stars and planets and gas and dust that make up everything familiar. We are, in a literal sense, in the minority. The universe is dominated by a substance we cannot see and do not understand. There are ideas about what dark matter might be. It could be made of some new kind of particle, something heavy and slow-moving and very weakly interacting with ordinary matter. Particle physicists have built detectors deep underground, shielded from cosmic rays, waiting for one of these hypothetical particles to pass through and leave a tiny signal. So far, no signal has been confirmed. Dark matter could also be something even stranger, something not made of particles at all. The honest truth is that we do not know. Dark matter is a mystery. It is one of the largest and most persistent mysteries in all of science, and it sits there, calmly in the data, waiting for an explanation. And then there is dark energy, which is a separate mystery with a confusingly similar name. Dark energy is the name given to whatever is causing the expansion of the universe to speed up. In the late 1990s, astronomers measuring the light from distant exploding stars discovered that the expansion of the universe, which had been known since the 1920s, was not slowing down under the pull of gravity, as everyone expected. It was speeding up. Something was pushing the universe apart, working against gravity on the largest scales. That something is dark energy. It appears to make up about 70% of the total energy content of the universe. Dark matter makes up about 25%. Ordinary matter, the stuff of stars and planets and people and beds and blankets, makes up only about 5%. We are, in a very real sense, a small minority in a universe we barely know. Dark energy is an even deeper mystery than dark matter. Its nature is almost completely unknown. The simplest possibility is that it is a kind of energy built into the fabric of space itself, a constant background energy that does not dilute as the universe expands. This idea goes back to Einstein, who called it the cosmological constant. He introduced it to keep his equations from predicting an expanding universe, and then he discarded it when the expansion was discovered, calling it his biggest blunder. But now, with the discovery of the accelerating expansion, the cosmological constant is back, and it fits the data reasonably well. But why it has the value it has, why it is so small but not quite zero, is a question that no one can answer. It is another open door, another dark room. So here we are, near the end of our journey, sitting with the not knowing, the weakness of gravity, the missing bridge to quantum mechanics, the invisible dark matter that shapes the galaxies, the mysterious dark energy that pushes the universe apart. These are not small puzzles, they are the frontiers of physics, and they are not going to be solved tonight. They are not going to be solved by any one person in a single flash of insight. They are the work of generations, of slow, patient, careful inquiry, of ideas tested and discarded and refined over decades. They are the landscape beyond the current map, and they remind us that science is not a finished book. It is an ongoing, open-ended journey, and not knowing is not a mark of failure. It is a mark of honesty. It is the willingness to say, here is where our understanding stops, and beyond this line, the world is still dark. This is a restful thing, if you let it be. It means that the universe is not a puzzle that has been completely solved, leaving nothing for future minds to do. It means that there is still mystery, still depth, still room for wonder. The gravity that holds you to the bed tonight is the same gravity that hides its deepest secrets from the brightest minds. It is both familiar and unknown, both simple and unfathomable, and you can let that duality sit with you in the dark. You do not need to resolve it, you do not need to pick a side. You can just let it be there, the known and the unknown, the understood and the mysterious, folded together like the stillness and the motion of the tides. Gravity is a force that does not quite fit, and that not fitting is not a problem to be fixed. It is an invitation. An invitation to stay curious, an invitation to stay humble, and an invitation to rest, knowing that the world is larger and stranger and more beautiful than any single mind can hold. An invitation to rest, knowing that the world is larger and stranger and more beautiful than any single mind can hold. That invitation leads us outward now, away from the puzzles and the open questions, and into the wide, calm space of belonging, because gravity, for all its mysteries, is also the great gatherer. It is the force that brought the universe from a nearly uniform cloud of gas into the rich, structured place we see today. It built the stars. It built the planets. It built the galaxies. And it did so slowly, patiently, over stretches of time so vast that the human mind can barely find a footing. In this section, we are going to widen the lens. We are going to look at gravity not as a puzzle to be solved, but as the quiet architect of everything we see, including ourselves. In the beginning, as far as we understand, the universe was very nearly smooth. After the Big Bang, the hot, dense fireball of energy and matter expanded and cooled. The matter was spread out, almost perfectly even, across the growing space. Almost, but not quite. There were tiny variations, small ripples in the density, places where the matter was a little thicker and places where it was a little thinner. These variations were minuscule, far smaller than anything we can perceive without instruments. But they were there, and gravity, patient and relentless, began to work on them. Where the matter was slightly denser, the gravitational pull was slightly stronger. More matter was drawn in. The region became denser still. The pull grew stronger. Over millions of years, This slow amplification turned the ripples into clouds, and the clouds into clumps, and the clumps into the seeds of what would become galaxies. Inside those forming galaxies, the process continued at smaller scales. Clouds of gas and dust, mostly hydrogen and helium left over from the early universe, drifted together under their own mutual gravity. The clouds collapsed inward, slowly at first, then faster as the material fell toward the center. As the cloud shrank, it heated up. The pressure and temperature at the core rose higher and higher. Eventually, when the core reached a temperature of millions of degrees, something new happened. The hydrogen atoms began to fuse together, turning into helium and releasing enormous amounts of energy. The cloud had become a star. The first starlight began to shine. This is how our own sun was born, about 4.5 billion years ago. A cloud of gas and dust, left over from earlier generations of stars that had lived and died, gathered together under gravity's patient pull. The cloud collapsed, the core ignited, and the sun began its long, steady life as a main sequence star, the kind of star that burns hydrogen into helium and shines with a steady light. The leftover material around the young sun, a swirling disk of gas and dust, began its own process of gathering. Small particles stuck together. They formed larger clumps. The clumps grew into rocks. The rocks collided and merged, building larger and larger bodies. Over tens of millions of years, this process of gentle accumulation, all driven by gravity, formed the planets. The Earth was one of them. The Moon came later, likely born from a giant collision between the young Earth and another large body, the debris from the impact gathering into a satellite that began its own long fall around our planet. Gravity did not stop there. It continues to hold the planets in their orbits, keeping them in a delicate, stable balance around the sun. Each planet moves along the curve of space, carved by the sun's mass. Each orbit is a free fall, an endless falling that never reaches the ground. The Earth has been falling around the sun for 4.5 billion years. The Moon has been falling around the Earth for almost as long. The tides have been rising and falling. The seasons have been turning. All of it, every part of it, is gravity at work. The same force that gathered the cloud is the force that keeps the Earth moving in its steady ellipse. The same pull that ignited the sun is the pull that holds you gently against the bed. And just as gravity holds the solar system together, it holds larger structures together as well. Our sun is not alone. It is one of an enormous number of stars, all bound together by mutual gravitational pull into a vast, rotating disk. This disk is our galaxy, the Milky Way. The Milky Way contains on the order of 100 billion stars. That number is hard to grasp. 100 billion suns, each one possibly with its own planets, its own moons, its own story. And all of them, every single one, is held in a loose, gravitational embrace with every other one. The stars near the center orbit the galactic center more quickly. The stars farther out orbit more slowly. The whole thing turns, slowly and majestically, completing one full rotation every 200 million years or so. The last time the sun was in this position relative to the galaxy, dinosaurs walked the Earth. The time before that, life was just beginning to emerge from the oceans. The galaxy turns, and we turn with it, carried by the same gravity that shapes the tides and bends the starlight. The Milky Way is not a solid object. It is a collection of individual stars, each moving under the combined gravitational pull of all the others. The shape of the galaxy, the beautiful spiral arms, the central bulge, the outer halo of ancient stars, all of it is shaped by gravity. The spiral arms are not fixed structures. They are density waves, regions where the stars are temporarily closer together, like a traffic jam on a cosmic highway. Stars enter the arms, linger for a while, and then move on. The arms persist because the pattern persists, a gravitational wave rippling through the disk of the galaxy. And the Milky Way itself is not alone. It is part of a small cluster of galaxies called the local group. The local group contains the Milky Way, the Andromeda Galaxy, and several dozen smaller galaxies. All of them are bound together by gravity. The Milky Way and Andromeda are the two largest members of the group, and they are currently moving toward each other, drawn by their mutual pull. In about 4 billion years, they will begin to merge. Their stars, which are so far apart that they will almost never collide directly, will swirl together into a new, larger galaxy. Gravity will reshape both galaxies, pulling their spiral arms apart and reforming them into something new. This has happened many times before in the history of the universe. Galaxies merge, gravity gathers them. The process is slow and gentle and inevitable. Beyond the local group, there are larger clusters of galaxies, and beyond those, superclusters, the largest known structures in the universe. The superclusters form a kind of web, a vast network of filaments and voids, stretching across hundreds of millions of light years. The filaments are where the galaxies are, strung like beads along threads of dark matter. The voids are where there is almost nothing, empty spaces hundreds of millions of light years across. This cosmic web is the largest scale expression of gravity. It is the final result of those tiny ripples in the early universe, amplified by billions of years of gravitational pull. From the smallest dust grain to the largest supercluster, the same force has been at work, gathering, shaping, holding. And now, as we begin to bring the lens back inward, we can trace this chain of gathering all the way down to you. The same gravity that shaped the cosmic web shaped the Milky Way. The same gravity that shaped the Milky Way gathered the cloud that became the sun. The same gravity that lit the sun formed the earth from the leftover dust. The same gravity that formed the earth holds the atmosphere around it, holds the ocean in its basin, holds the moon in its orbit. And the same gravity holds you, right now, in this bed, in this room, in the dark. You are not separate from this story. You are a part of it. The atoms in your body were forged in stars that lived and died before the sun was born. Those atoms were gathered by gravity into the cloud that became the solar system. They were gathered again into the earth, and they were gathered, over the course of your life, into the body that is now resting here. Gravity has been part of your existence from the very beginning, long before you had a name, long before there were names for anything. This is a deep kind of belonging, not a belonging to a place or a nation or a family, although those things are real, but a belonging to the universe itself, a literal, physical connection to the stars and the galaxies and the vast web of matter that stretches across the sky. Gravity is the thread that ties it all together. It is the force that has been gathering things since the beginning of time, and it has gathered you, too. You are held by the same pull that holds the Milky Way together. You are supported by the same force that shapes the orbits of planets. You are part of the same great, slow, patient process that has been unfolding for billions of years and will continue for billions more. As you lie here in the dark, you can let that sense of belonging wash over you, not as a fact to memorize, but as a feeling to rest in. The weight of the blankets is the weight of the galaxy. The pressure of the mattress is the pressure of the cosmic web. The slow rise and fall of your breath is the same rhythm that moves the tides, that turns the seasons, that spins the galaxy. You are not a small, isolated thing in a vast, indifferent universe. You are a piece of the universe, gathered by gravity, held by gravity, connected by gravity to everything else. The stars are your distant relatives, the galaxies are your larger home, and the bed you are lying in is a small, quiet corner of a cosmos that has been shaped, from top to bottom, by the gentle, patient, unceasing pull of gravity. Let that be enough. Let that be more than enough. The story of gravity is not just a story of forces and equations and curved space. It is a story of gathering, of belonging, of the slow, steady work of bringing things together. And you are part of that story. You have always been part of it. You will always be part of it. The gravity that built the stars is the gravity that holds you now. The same pull, the same force, the same quiet, endless embrace. And as we drift toward the very end of our journey, we will carry this sense of belonging with us, letting it settle into the silence, letting it soften into sleep. And so we arrive at the final quiet stretch of our journey, the end of the path. If a path this winding and gentle can be said to have an end, we began with the weight of blankets, the simple bodily sense of being held. We moved through falling and floating, through spinning and orbiting, through curved space and bent light and slowed time. We visited the tides and the black holes and the open questions that no one has yet answered. We widened the lens to see gravity as the great gatherer, the force that built the stars and the galaxies and the planets, the force that connects you to the entire cosmic web. And now, as we prepare to let all of that go, we are going to do something very simple. We are going to return to where we started. We are going to come back to the body, to the bed, to the dark, and we are going to let everything we have touched on settle, softly, like dust falling through still water. Gravity is both the simplest force to feel and one of the least fully understood. That thought has been with us from the beginning, and it remains true. You do not need a degree in physics to feel gravity. You have felt it every moment of your life. It is the first thing you knew, before words, before memory, before any conscious thought, the pull toward the ground, the weight of your own body, the resistance of the floor. These sensations are so constant, so ever-present, that we stop noticing them. They become the background, the baseline, the silent ground note of existence. And yet, when we turn our attention to them, when we really sit with the fact of gravity, we find that it contains entire universes of depth, from the falling apple to the bending of starlight, from the ocean tides to the event horizon of a black hole, from the clock on the wall to the satellites overhead correcting for the curvature of time. All of it is one thing. All of it is gravity, and all of it is happening, right now, in the quiet space around you. You are lying in a gravitational field. The earth is curving the space and time around you. Your body is following that curve, sliding down it, and the bed is pushing back. That push is what you feel as weight. The blankets have weight because the earth is pulling on them, and they are pulling on the earth in return, an equal and mutual attraction that has been going on since the blankets were made, and will go on until they are unmade. The air in the room is held close by gravity, and you breathe it in and out, and the rhythm of your breath is the same rhythm that moves the tides, slow and steady, in and out, rise and fall. The moon is out there somewhere, pulling on the oceans, pulling on you, a gentle presence that has been with the earth for most of its history. The sun is on the other side of the planet, holding the earth in its orbit, a free fall that has lasted 4.5 billion years and will last for billions more. All of these things are true at once. They are not competing for your attention. They are not asking you to understand them or remember them or do anything with them. They are just there, like the dark itself, like the quiet, like the slow beating of your own heart. Gravity is the thread that runs through all of them. It is the reason the blankets rest against your legs. It is the reason the bed does not float away. It is the reason the earth does not drift off into the cold of interstellar space. It is the reason the sun shines, the reason the galaxies turn, the reason the universe has any structure at all. And it is also the reason you are here, now, in this moment, resting. Gravity gathered the atoms that make up your body. Gravity gathered the planet that supports you. Gravity gathered the star that warms you. You are, in a very literal sense, a child of gravity. We all are. And yet, for all its ubiquity, for all its importance, gravity keeps its secrets. It is far weaker than the other forces, and nobody knows why. It does not fit neatly with quantum mechanics, the physics of the very small. What happens at the center of a black hole is a mystery. What dark matter is, what dark energy is, these are mysteries too. The universe is larger and stranger than our current understanding can hold. And that is not a failing, that is a gift. It means there is still more to discover. It means the world has not been fully mapped. It means that wonder is still possible, that the unknown is still out there, waiting patiently for future minds to find it. You can rest in that not knowing. You can let it be a comfort rather than a frustration. The universe does not owe us all the answers. It gives us enough. It gives us the stars and the tides and the weight of blankets and the slow curve of space around a massive object. It gives us enough to be curious, enough to be humble, enough to be still. So now, as we come to the very end, let us return one final time to the image that opened this journey, the weight of your body in the bed. But now you can feel it differently. You can feel it as the mutual pull between you and the earth, a conversation between two masses that has been going on since you were born. You can feel it as the curve of space and time around the planet, the gentle slope that you are sliding down, the bed pushing back against you. You can feel it as the same force that holds the moon in its orbit, the same force that bends starlight, the same force that slows the clocks on satellites. You can feel it as the force that gathered the cloud, that became the sun, that built the earth from cosmic dust, that shaped the Milky Way into a spinning disk of 100 billion stars. All of that is in the simple sensation of being held. All of that is in the quiet pressure of the mattress against your back. The cosmic and the personal are not separate. They are the same story, told at different scales. Gravity is the teller of that story, and you are part of it. Take a slow breath. Feel the air fill your lungs. Feel the weight of your chest rise and fall. That weight is gravity. That breath is possible because gravity holds the atmosphere close. Let your muscles go slack. Let the bed take your full weight. You do not need to hold yourself up. Gravity is doing that work. It has been doing that work your whole life. It will continue doing that work long after you have fallen asleep. You can trust it. You can surrender to it. You can let go. And as you let go, you might imagine yourself slowly drifting the way the astronauts drift in the space station, not because gravity is absent, but because you are falling freely. Drifting the way the Earth drifts around the sun, in a smooth, silent, endless arc. Drifting the way the galaxy drifts through space, carried by the pull of other galaxies, moving in the great cosmic web. Drifting the way a feather drifts in a vacuum, side by side with a hammer, falling at the same rate, light and heavy together, no difference, no hurry. Drifting the way your thoughts drift as sleep approaches, one idea blending into the next, the edges softening, the sharp lines fading, drifting, weightless. Not because gravity has gone away. It has not. It is still here, still pulling, still curving the space around you. But you are no longer resisting. You are no longer holding on. You are letting yourself be carried, the way the ocean is carried by the moon, the way the earth is carried by the sun, the way the galaxy is carried by the gravity of all its stars. You are part of that great, slow, patient motion. You have always been part of it, and now, in the quiet of the dark, you can feel it, not as a thought, not as a fact, but as a sensation, a gentle drift, a soft floating, a quiet release into the arms of the force that has held you from the very beginning. The blankets rest against you. The mattress supports you. The earth pulls on you, and you pull on the earth. Time flows a tiny bit slower here than it does high above. Starlight bends as it passes through the curved space around the sun. The tides are rising and falling somewhere under the moon. A black hole sits at the center of a distant galaxy, its shadow ringed with light, its center unknown. Dark matter shapes the cosmic web. Dark energy pushes the universe apart. Gravity is at work in all of it, the quiet, steady, unceasing force that does not fit and does not need to fit. It simply is. And you simply are. And that is enough. Let the words fade now. Let the ideas drift away. You do not need to hold on to any of them. They have done their work. They have kept you company through the dark, and now they can go. What remains is the weight, the warmth, the slow rise and fall of your breath, the soft pressure of the bed, the quiet of the room, the dark behind your closed eyes. Gravity is holding you. It has always held you. It will always hold you. Rest in that. Drift in that. Let the world turn beneath you. Let the galaxy spin. Let the universe expand. You are safe. You are held. You are home.